Aujourd'hui, on accueille Maurine Montagnat, qui est directrice de recherche CNRS à l'Institut des géosciences de l'environnement et qui travaille sur la mécanique de la glace. Je te laisse la parole directement pour le séminaire. Merci.
Merci. Merci Anaïs pour l'invitation. Thanks Anaïs for inviting me. I was asked to give the talk in English because some people here are not speaking some French, so I hope it's fine for everyone. So the talk I've prepared here is a talk that I've given already at MECAMAT in January. So maybe some of you have already seen it, and I'm sorry for that. It's quite a wide scope. It's not a deep focus on ice mechanics. It's more where does ice mechanics, what is the context of ice mechanics? What do we need it for? And mostly in relation with polar ice sheets and climate. So maybe some of you will have some more questions after that related more to material aspect or mechanic aspect, but we'll see. So well, let's have a look and let's make some kind of a journey inside a deep ice core. So polar ice caps, I think I don't need to introduce them here. So mostly Greenland and Antarctica are where we get access to these deep ice cores. And why are we interested in is mostly because climate archives into the ice. So climate archives into the ice for several reasons. Because of accumulation and ablation, where in deep ice core, in area where we dig the deep ice core, it's mostly accumulation. It also archives because of flowing, so flow mechanisms. And it archives also through interaction with the ocean. So in fact, those big ice sheets are an overall climate indirect signal somehow. And where we dig deep ice core is most of the time in the central part of Greenland or Antarctica, where the accumulation is the lowest, and therefore we have the longest climate time that we can recover out of it. Or we can also dig them on places at the side, because we want to know more about flow mechanisms, for instance. So less interested about the oldest climate history, but more about flowing mechanism, interaction, and so on. So there are many coring sites that exist. I've just drawn a few of them. Those are the ones that I've been involved in, for instance, some of them actually. Here you have the very well-known, can you see my, yeah, I think so. Would you have a pointer actually? Or no? Okay, that's okay. Ah oui, bah ça c'est parfait. The best pointer on earth. So here is Vostok. So Vostok, maybe, I don't know, who knows about the history of Vostok and the climate history that's, okay, great. Usually everybody knows, so I'm happy that I can teach you that. So Vostok is a place where I would say the first climate history has been measured. It was in the late 80s, early 90s. The history is quite interesting because in Vostok it's a Russian site, and during the Cold War, in fact, Russian had digged a very long ice core there, but they didn't really know what to do of it. What they wanted to know is what was behind the ice and maybe some, resources like petrol or oil or minerals and stuff like that. And they met with some French researcher like Claude Lorius. I guess you've heard of him. And Claude Lorius had this, or not only him, but Claude Lorius and his colleague had this idea that maybe the climate was stored in these deep ice cores. And he managed to organize something between USA, Russia, and France to get access to the core, to bring it back to Paris, and then to study them. So in the middle of the Cold War, it was quite impressive. So here we got the first knowledge about the fact that climate could be stored in a deep ice core. And then from Dome C, more recent core, early 2000, we'll see about it, we got the longest climate history. And very recently, like last winter, they went to dig again at Dome C and they got a record of more than 1.2 million years of climate history. So that's the place. Berkner Island is a funny place because it's a very small island, so it's taken as an example of a small cap where we think we can understand better. And then in Greenland, we dig deep ice core there too, but because the accumulation is higher than in Antarctica. Here in Antarctica, like Vostok, Dome Sea are desert. So there is about 2 centimeters of snow accumulating every year, so it's very little. And here in Nîmes or North Grip Gibbs, there is about 20 centimeters of snow accumulating every year. So the yearly signal is much better resolved, but we get to a much shorter time in Greenland. I'm getting too fast. Just a view of Vostok, Antarctica. So the old station there from the Russian, former Russian team. And here you are in Dome Sea, Antarctica, just to have a view of that. In Dome Sea now we have a permanent European station that's called Concordia. And so there in this building people can stay all year long, being isolated from the rest of the world between March and November, because there's no access possible at this period of the year, or May to November, let's say. Okay, so what about the story of a deep drilling? So different steps. So here is the example of the first Epica Dome Sea very long ice core. Just to tell you that we don't do that in 1 month or 1 summer, but we need to do that in several years. To go in Antarctica and to do this deep drilling, we can only do that at the summer period there, so winter for us, and it's quite often 2 to 4 months per working period. So, for instance, at Dome Sea, so there was a casing, so the hole where the drill is going to be made is prepared in 2000, and then different steps. So first, DC1 is because the driller got stuck at some point, so they had to stop drilling there and do another hole. And then only in 2004-2005 did we get access to the very deep ice, where we got this longest climatic history at the time. Another view of, here it's Nîmes, so another site in Greenland where I've been. And so those are more recent camp. Here it's a camp that can be moved. So it has been moved to North Grip, to East Grip a few years ago. So here is, you can see the preparation of the hole. So why do we need to prepare the place where we dig the hole? Is because in the big hole, in the drilling hole, we put some kerosene or liquid that has to be at higher density than ice, so that the hole remain open for several years. Otherwise, because of the flow of ice, the hole is going to get closed. But then it's a liquid that should not get frozen at -50 degrees. And we don't want this liquid to go through the snow, so we have to dig a first hole just until we get access to firn with a high enough density that we can put the liquid in the hole. Well, that's a big story. But then we get a deep ice core like that. So every deep ice core, every ice core is going to be about between 1 to 3 meters long. And so to dig until 3,270 meters, then you can imagine that you have to put the driller in the hole, you get your core, you get it out, you get the ice out, and then you go back to the hole, you get it out, and so on. So you just do step by step, and this is why it takes a lot of time. Here are some cores that are being stored. Out of this core, we are going to make many measurements. But me, for instance, I do some thin section of ice. I will come back to that, and I get access to the microstructure in terms of crystal orientation and size, for instance, or shapes, or whatever we want. But as I've just said, we can measure many different things in the deep ice core. So we measure what is very well known, like water isotopes that give access to temperature. We were going to measure where are they? The gas. So here are the gas that are being measured in this part. So from the gas, we get access to greenhouse gases. We are going also to measure cosmogenic isotopes to get some direct datation. What else? Dust, chemistry, and the famous physical properties famous for me, because those are the ones I'm interested in, who tell us about how the ice has been deforming. Okay, climate of the past is the main story about that. This is not the only one, but that's the main story about it. And so here I've plotted in scale of age, so down to 700,000 years, So the Vostok ice core, as I told you already in maybe the late 90s, early 2000, gave us a signal until about 400,000 years of climate history, where we can see that, okay, nowadays we are in a warm period, what that is called the Holocene, but 20,000 years ago we were in a cold period that lasts about 80,000 years ago, and then another warm period, another what we call interglacial. Well, this one was called Aemian, and so on. And so during those 400,000 years, we had 4 cycles of warm, cold period, like that. With Epicadome-C core, we could get access to this cycle of, here is the temperature, until close to 800,000 years. And now is being studied the rest of the core that should go back to 1,200,000, well, we understood, 1.2 million years. The big story of that was also that thanks to the deep ice core, we were able to relate the temperature at which the snow fell onto the ice core to the contents of greenhouse gases. And therefore, from that, the first paper in 1991, I think, oh, sorry, I don't remember, made this relationship between the temperature on Earth and the amount of greenhouse gases that was also at the surface of Earth. And of course, we know that now we are getting into trouble because we are reaching some content of greenhouse gases, in particular CO2, that are much higher than 400 ppm per volume, and that are about more than twice as high as what has been measured for the last 800,000 years. So we know somehow, and we already measure it, that the temperature is going to follow. We just don't know how fast and how much. So the CO2 and the methane are recovered in the bubbles here of the ice, contained in the ice, and the temperature is less direct measurements. It's recovered by means of the water isotopes. So there is a relation in what we call the thermometer, the isotopic thermometers, a relation between the deuterium content and the temperature. So those are based from surface measurement, and they were quite fine. And they enable us to get from the ice, this time, not the bubbles, but from the ice, and the water isotope in the ice, we can get access to the temperature at which the ice fell. Then it's not the only story, because what you can see here is only the depths at which the sample, the ice was recovered. But then we have to turn this depth into some datation. So we have to say, what was this age? Okay, no, here is the age, but in fact what we have is just a depth, and so we have to turn from depth into datation, and it's not a direct mean. And I will go quickly on that. And another interesting thing, at least for me, that's working on how ice is deforming, is that from a view from satellite, we can see that the ice is flowing. So, of course, in the area of Dome-C and Vostok, the speed of the way the ice is flowing is very low. So here is a meter per year. But when you go to the ages, like, for instance, here in the area of Dumont-d'Urville, the ice is flowing much faster through what we call ice streams. And ice streams are some very important feature now, because we know that most of the ice that is escaping from the big ice sheet is escaping through ice stream that transform later into icebergs and flow into the ocean. And the velocity of those ice streams are strongly related to climate warming. Okay, so as I said, from the ice sheets, we can get access to the climate of the past. But for that, we have data from the core, but we need ice sheet flow modeling to extract, to connect the depth of the core to the datation. And then we can also predict the ice sheet evolution in a warming climate. But to go from this warming climate to the future of ice sheet, we also need ice sheet flow modeling. So in flow modeling, there is the word flow. And for that, we need to know about mechanisms that are behind it. And in particular, we need to know the physical processes of deformation of ice. And this is where my work is standing, because there we can, so from deep ice core, we can access to microstructure, to texture, so crystallographic orientation, and that will tell us about the deformation mechanisms and also the stress field that the ice, or at least an idea of the stress field that the ice has been experiencing. And those data are directly put thereafter in ice flow modeling. Another aspect that I won't deal with is the densification, and also what's going on is the very bottom part of the ice core where we have perturbation, but where most of the deformation is occurring actually. Densification is very important because so ice is falling in the shape of snow, and then it densifies, it goes to firn, and then it goes to ice. But there is what we call, there is a period where the air that is contained into the snow and the firn is still in contact with the atmosphere, while the ice is holding somehow. It's getting older and older also here. So if you go, for instance, here, when you still have porosity, you have air that is today air, for instance, but the ice is already old and can be up to in the current atmospheric condition, 5,000 years old, for instance. So there is a delta H between the ice and the air. And if you remember well, CO2, methane are measured in the air, while temperature is measured in the ice. So there is a delta H that we are able to measure nowadays, but we don't really know what happened in former time. So there is many people that are studying densification to get access to this delta H and to correct or to make sure that they really well superimpose the H and the temperature, I mean, and the CO2 or the gas concentration. Ice sheet flow modeling. So big ice core are modeled. So as I said, they are flowing, and they are flowing mostly because ice is considered as a fluid with a viscoplastic behavior. And so the way we model it is through Stokes equation, to which we will add this relationship between stress and strain rate, I would say, to be more correct. So we need to get access to this viscoplastic behavior and the law that we have to put in it. And for that, we need to know the rheology of ice. We need to have information about the texture, so the crystallographic orientation. And we need to know about mechanisms that are making them evolve. So, for instance, in ice recrystallization, dynamic recrystallization is very active. So we study ice at this polycrystalline scale, and then we go also down to a single crystal scale to better understand all those mechanisms. Today, I will skip on this scale here to make the link between what we know about the polycrystal and what we have to put in the flow law for large-scale flow modeling. So how do we measure microstructure and texture in ice? So I stated briefly already. So we start from an ice core and we do a thin section of ice. So you see the scale of thin section of ice. They are quite big. You see, so there are several centimeters. So about 10 centimeters here, 8 to 10 centimeters here. Why? Because our crystals are big, relatively big compared to many other materials. So from this thin section of ice and from observation between cross-polarizer, we can get access with a specific analyzer to the crystallographic orientation of the optical axis. So ice is a crystallographic material, hexagonal with an hexagonal crystalline structure. And the optical axis is the axis of the big axis of the hexagon. I'll come back on that, I think. And so those are the information that we want to recover. So here it is. So here is the crystallographic texture, crystalline texture of ice. And this optical axis is the c-axis, so the big axis of our hexagonal structure. And so from this analyzer through thin section for each crystal, so each color here, we get access to one orientation of this c-axis. And it's quite good for us because in differently oriented. Yes, oh yes, I forgot to say that ice is a monomineralic material. Merci. So we have mostly one mineral that is ice. So yes. Okay, so we do these pole figures, and from that we can see whether the crystallographic orientation are isotropic or whether they are anisotropic, and the two main shapes we can obtain are either a big cluster like that or a girdle like that. And so we can also characterize this different type of crystallographic preferred orientation by means of orientation tensor. It's just a value that tells us how much isotropic is or distribution of the axis orientation and how much of a cone or how much of a girdle it is. So this is the way we use it. We can have some more information about it, but we will use it that way. And here I will give an illustration of some measurements that I've been doing at the Nîmes ice core here, Nîmes. So Nîmes is, so very top of Greenland is Grip. And then here there is a ridge going through the Greenland northwest side. And Nîmes is here. And what is interesting about Nîmes is that due to its configuration, it deforms mostly by compression and by shear in the last third of the core. Just to give you some view of what we are talking about, vertical strain rate, so let's say for compression, for the compression part, is 10 to the minus 10 per second. So yes, please?
How do you know that
no, we don't know from satellite. We know from the geography of the area, so from what we know from the bottom, from the bedrock, but also we know from the texture, from the microstructure and texture that we are measuring. I will show that just later. And so vertical strain rates are very low and deviatory stress is very low too. So if we were to do an experiment in the lab with this same characteristic, it would take about 30 years to get 1% strain. So we have a very hard time to redo this type of configuration in the lab. Just to show the condition of work at Nîmes. So here is the surface, and we work in a trench, a scientific trench, because we want to work at low temperature. We want to make sure we work at temperature close to -10 because we are working on ice all the time. And so we dig a trench and we go down through this trench by some stairs, and then we work in the cold all day long. So to make this analysis, so the thin section analysis all along the core, at the time, we did one thin section every 10 meters, so it's about 250 thin sections. Each thin section takes about 15 minutes when we are fast. So we have been working on that during 2 seasons because it was too long. Okay, here part of the answer to the questions that I've just had. So then all over the core, so here at Nîmes, we went down to a little more than 2,500 meters. We can see the evolution of the microstructure, so crystal size and shape somehow, and the evolution of the crystallographic preferred orientation. So what we can observe here, we are 33 meters, we are still in the fern, so there are still some bubbles or some, it's quite a porous material. And then the deeper we go, the less bubble we see, the crystals are growing. Until about are growing and getting more and more getting a texture that is more and more anisotropic. So here we see some track already of dynamic crystallization, and once in a sudden, around 1,500 meters, the crystals are becoming very small and all the same color because more or less all oriented the same. And I will come back on the explanation of that. And then when we go deeper, the crystals are getting very big. So you see the little square here is 1 centimeter square. So we have crystals of more than 10 centimeters. We are not even able to measure them with our thin sections. So that tells us a story somehow. So what kind of story does it tell us? It tells us that, okay, we have some viscoplastic deformation, mostly in compression. I won't show exactly the details actually, but I can show it later, how we know it's compression and shear. But I can explain later. And we know that from the shape of the crystal here, we do have some dynamic crystallization already quite active because the shapes are not rounded. So there are a lot of grain boundary migration. There is a lot of grain boundary migration. And then how do we explain the shift, the big shift? Is because we are entering in an area where shear is dominating the deformation, and in the same time we have a change in climatic origin. And what does that matter? Is because this ice is from Holocene, so warm period. This ice is from the previous glacial period. And during the glacial period, there is even less amount of snow that is falling every year. So in every layer of snow, there is a higher amount of dust, of impurities. And those impurities, they are prevent dynamic recrystallization mechanisms to occur. And so this ice will be, grain boundary migration will be less active, and this ice will be even more sensitive to shear. And the interesting thing about NIM is that both appeared in the same time, that we have a configuration that's favorable for shear, and we have the climatic origin that is changing more or less at the same depth. So that's quite interesting for us. And then deeper in the ice, we are getting to warmer temperature. So close to the bedrocks, temperature can go to 0 degrees. And so every recovery mechanism are much faster. So dynamic recrystallization may become fast, or fast at the scale of what's going on there. And this is very likely why the crystals are getting very big. Why are we interested also into that? It's because of the modeling of flow. So when we have, like in Föhn here, some textures that are more or less isotropic, it's not that true, but it's at the first order it is, then the mechanical behavior of this ice is isotropic. But where we get to this kind of ice with a very strong anisotropy, then the mechanical behavior is also very highly anisotropic. And then at the end, where most of the deformation is taking place, at the interaction between the bedrock, we get back to mechanical behaviors that we can assume to be quite anisotropic. So in fact, both mechanisms of deformation, so the viscoplasticity is responsible for those texture to happen, and the dynamic recrystallization that is also responsible from some specific texture to happen, have some impact on the flow. So it has been modeled. So here is a simulation of texture evolution around the grip ice core. And you see that if we take into account the possibility of texture to evolve into the large-scale flow modeling, then we are able to simulate that we start from a nearly isotropic ice, and we get to a very concentrated texture, so a very anisotropic ice. And from what we observe, we can say also, so this answers the question before, which kind of mechanism we had. So when we have this type of texture in the shape of girdle, so this is what we observe in Vostok, for instance, we know that the ice was submitted to some tension, uniaxial tension mostly. And this can be explained also by the shape of the area where the Vostok ice core was drilled. And when we have this kind of very concentrated texture, we know that ice has been mostly deformed by compression or shear. And we can decipher between the two. Sometimes we do that by means of modeling. So for instance, we use a viscoplastic self-consistent modeling to predict what we should have with only compression and what we should have with shear. And then we can more or less make some assumptions. So as I said, texture is evolving with flow, and texture is impacting flow. So we have to take them into account in large-scale flow modeling. Okay, I will come back on that at the end, but then what do we know also? So we've seen that dynamic recrystallization is very active in deep ice core. What can we learn from laboratory experiments from this mechanism, this specific mechanism, and what is going on? And so this is the example I'm going to take of some experiments that we are doing in the lab. So in the lab, we are building some ice that from which we can control the microstructure, and we are deforming it. So very simple, creep test at a given load, given temperature, but always a temperature that is much warmer than what we have in natural condition, just because we need it to be fast enough. A PhD cannot wait 30 years to get 1 point in a curve, so we need to be faster. And then we can see that when we go faster, we do have access to some very big changes in microstructure, like new small crystals that are being formed, lattice misorientation inside the grain, so all typical mechanisms of dynamic recrystallization. So for those who are not familiar with this type of mechanisms, so during viscoplastic deformation, Deformation is occurring by dislocation interaction, dislocation creation and interaction. So those are linear defects that makes the viscoplastic deformation possible. But those are defects, and therefore they accumulate some strain energy. And to relax this strain energy at relatively low strain rate, then the microstructure is going to change in order to absorb some dislocation density, so that we reduce the amount of dislocations that we have. The way it works is that either by grain boundary migration, so grain boundary is going to migrate and will absorb some dislocation, or by nucleation, so we are going to create new grains that are going to make use of the existing dislocation to be created. And so this is why there is where the stored energy is what explains these changes of microstructure during deformation of materials like ice. Yes, please? What do you mean by dislocation are in fact, a dislocation is when you have a full plan of atoms that are missing or molecules that are missing. And therefore you have, this is a linear defect, you have some kind of a plan that stops instead of, and so it's a line. Is it, okay, I should have put a graph actually. Yes, we also have, because there is also some point defect, so when an atom is missing, and a grain boundary is a 2D defect, so planar defect, not plan, but 2D defect. How do we follow dynamic crystallization in ice? So we can follow dynamic crystallization just by looking at the microstructure, as I said before, grain size, shape, and orientations. But we can also follow it by making some model experiment and trying to relate the strain field, so the deformation that is taking place at the crystal scale or intra-crystal scale, related directly to the misorientation before and after the test. That's a good thing about ice, because ice is a material that we can easily create in the lab. And in particular, we can create 2D.5 materials, so columnar materials with columnar crystals in one direction. So here you have typical material granular structure, and then you have a column. So when we observe this one face of our materials, then we have information, or we suppose that the information is more or less representative of what's going on in the depth, because of the grains being the same in the depth of our sample. So we are able to do big samples like that, and then we put a speckle on our surface. We take images regularly, and we correlate those images, so by techniques that are quite well known now, and we get access to the strain field, so how much displacement or strain has occurred where. And then we can relate it to the mechanisms microstructure at the microstructure scale. So I will show just one example, short example here. So here we really wanted to focus. So at that time, we didn't have so good, so there are cameras that are much better now, but at the time, we wanted to study a triple junction here, and since our dimensions are quite big, we made a focus on it. And we wanted to see how the strain field was evolving when we had this new microstructure forming by recrystallization. So it's before deformation, after deformation, only 3% of strain, so it's quite a low deformation, but you can see that already after 3%, here we have new grains that appeared, and we had also high angle subgrain boundaries that have been formed. So the microstructure here has changed a lot. So what is going on with the stress? So we can see that the stress is concentrating at first at triple junction, and then as soon as some new structures, so grain boundaries or subgrain boundaries are appearing, the strain is going to concentrate around these new boundaries. And therefore, we can follow with strain or with time the appearance of those new structures. And so here we see, for instance, the appearance of the new grains. And then here we see the appearances of subgrain boundaries. So we can see that dynamic recrystallization has the effect of reducing the very local amount of strain and spreading it over space. So that's really a way to enable more deformation to occur in this area that was probably highly constrained. So I don't go too much into detail, but and then we can also study the mechanisms, the basic mechanism of dynamic recrystallization with electronic microscopes. So here it's EBSD observation, so where we can have this time not only the C-axis, so the optical axis orientation, but the full crystallographic orientation of at a quite good resolution. I don't remember the resolution here, but then we can have access to subgrain boundaries in red here and the real orientation of our grain. From that, here, for instance, what we have measured is a relationship of orientation between the parent grains, so the grains that were here before dynamic recrystallization, that are here in orange, green, yellow, and brown, and the new grains that have been formed during this process of dynamic recrystallization that are small grains at the grain boundaries. And so by plotting them on a pole figure, we can see that most of these new grains have orientations that are closely related to the parent grains. So dynamic recrystallization, at least here, did not create any new orientation, but just a spread of orientation to ease the deformation in this area. Okay, so to finish with, maybe let's go back to modeling. So as you've seen, we are able to study at the polycrystal scale and even at the smaller scale the mechanism of textures, the mechanism of recrystallization, and then we have to transform that in order to put that into some rheological flow laws so that we can feed the large-scale flow modeling. We are not that far so far, but we still lack some information. And I will give you just a short example here. So most of the, well, maybe I have to precise that. Most of the flow modeling we are having right now are considering that the ice is isotropic because it's much easier. Otherwise, the anisotropic flow law here get much more complicated, and so the calculation time is more complicated. So far people were thinking that, okay, we can consider ice as isotropic. Anyway, there are much more other problems to fix, like what is going on at bedrock. What about taking into account, having a good account of the accumulation? What about what is going on at the interface here with the ocean, which is a hot topic in my community? And so we left at the side the question of the anisotropy of the ice. But more recently, and especially when we are considering glaciers, alpine glacier or ice streams that are flowing very fast with a lot of heterogeneous stress field, we are starting reconsidering this question. And I will show just here a very brief example, some recent results. Here we are on the Plan-Pincieux glacier. So by there, I think there are the Grand Joras. And here we are from the Italian side of the Grand Joras face. And the glacier is here. So this glacier has been studied by the Italian for a long time because they are very scared of this amount of ice, unstable ice, to fall on the Plan-Pincieux village that is below, and that could put a lot of problems. So they have been cutting the road, asking people to move away from the village several times already within the last 10 years. So far, so good. But anyway, people are making some measurements, many different type of measurement, and we took advantage of that to do some surface scoring to see is there any texture, is there any anisotropy in those glaciers that are flowing very fast, that are also where ice is temperate, so at 0 degrees, very close to the melting temperature? What's going on? Do we have to take into account this anisotropy in ice flow modeling? And the good thing about it is that, well, we were lucky because already on the very surface of ice, so those cores were 60 centimeters long, so very top cores, we could measure some texture, some anisotropy that is non-negligible, in particular here, where you can see that the crystallographic axes are well concentrated. And we could also explain the texture we are observing based on surface velocity measurements of the glacier. So here you have one part of the glacier, another part, and they are gathering together here. And here it's an area where the two parts of the glacier are gathering. And we could analyze this texture based on what those flow lines, surface velocity, tell us about what's going on. And maybe I can take just one example. Okay, let's take this example. The texture is not very strong, but still it exists. It's number C. And here C is more or less in the middle of the larger part of the glacier that we see here. So it's here, in a part that is flowing quite smoothly. But it's flowing on a slope, and therefore the main deformation that this ice is following is shear. And the texture that we are measuring is in a very good agreement with the amount of shear that we are expecting in this area. Good point for us. What about this one here? So it's B, we are just here. Why is the texture oriented that way? Wow, okay, we had to try to explain that. Okay, B is here, and so there is some big slope, steep slopes here at the side, and therefore the ice is what we call at a shear margin, and it's not only submitted to the horizontal shear, but it's also submitted to some lateral shear because of the ice being blocked by the the cliffs that are there. And the good thing is that, once again, here the texture is very coherent with some lateral shearing here. So we were quite happy about that. And then we were also able, so from viscoplastic self-consistent modeling and from some also full field modeling, we were able to estimate the increase of fluidity that would create this kind of texture here. So if we are to put an isotropic ice in a flow model, or let's say a viscoplastic self-consistent model, we would have a given answer. But if we put this type of texture in the same model, we must deform it by shear, we see that we can have more than twice increase in fluidity. Yes, and that's? Those are measurements. But from those measurements, we take the texture, we put it into a self-consistent model, viscoplastic self-consistent model, and we can estimate the answer of our polycrystal and see how more fluid it is or how less fluid it is. Does that answer your question? Okay, great. And so we get to the point that maybe even in fast-flowing glacier, alpine glacier, we cannot neglect this anisotropy, and that we really have to go toward an anisotropic flow law, although it is more complicated. So there have been some attempts last year, but now we are getting back into this work, and I'll tell you more next time, maybe. So, well, now take-home message, if I could try. So I hope I have convinced you that analyzing physical properties along ice core is necessary to understand and simulate ice deformation in natural conditions. Large-scale ice sheet models are necessary to interpret climatic data, so by means of datation, and to predict ice sheet evolution in a changing climate. Then modeling mechanisms at large scales requires the knowledge at small scale, so this is why we are doing some lab experiments, but also physically based model, as we've seen, models that, for instance, are able to account for the ice anisotropy, and then some scaling method. How do we go from the lab to the large scale at a cost that is not too high? So this is where we are, and maybe more next time. So thank you for your attention.
Thank you very much for the nice talk. Do you have any questions?
Merci. Je pose en français.
Oui, je pourrais répondre en anglais peut-être.
Pour revenir, tu as dit que si tu considères une microstructure isotrope, du coup, c'est moins fluide. Quand tu considères l'anisotropie, tu augmentes la fluidité. Ça pourrait être l'inverse.
Oui. Yes. So when I consider, what I said here is that this texture is more fluid than an isotropic texture if we deform it by shear in the condition where we suppose it has been deformed. But if we deform it by compression, for instance, a compression like that, then this texture is much stronger, less fluid than an isotropic one. So of course it depends on the boundary condition, yes. Thank you for the question.
Une question?
Thank you for the very nice presentation, and perhaps this is a bit technical, but what kind of viscoplastic model do you use for the ice?
Okay, so I've been working for a long time with maybe VPSC, so viscoplastic self-consistent model. So we are considering, so on this model, for instance, the good thing is that we are able to put the different slip systems. So we are considering basal slip system, prismatic and pyramidals. but knowing that we have absolutely no proof of the existence of prismatic and pyramidal slip system based on experiments. So it's more a trick somehow we know that we mostly have basal slip, and maybe we have something else and we put it onto prismatic and pyramidal slip systems. So that's one way to model it. And more recently, we have also developed some finite element modeling based on orthotropic flow law. So a flow law that was considering only the anisotropy in the direction of the crystallographic axis and isotropy in the basal plane. So it's a little simpler model that's probably better adapted to large-scale modeling. And it was also simpler to put dynamic crystallization into the modeling, because with viscoplastic self-consistent, at least the one we use, we don't have dynamic crystallization. So does that answer your question? Okay, great. Thank you.
J'avais une question d'un point de vue très naïf. J'avais vu que c'était beaucoup contrôlé par la loi de Glen's law.
Oui, Glen's law.
Et comment, est-ce que ça vaut encore aujourd'hui? Est-ce que comment vous le voyez
Alors, so the Glen's law is a law that have been from some experiment made by Glen in 1950, 52, 55, or this area. So Glen, he took some polycrystal of ice, he made some creep experiment, just put a load on top of it, and he measured the creep curve. And the creep curve in ice, maybe I can draw it here quickly. I don't know what time is it, so please stop me when it's too late. So the creep curve in ice gives you something like that. So here you have the strain rate, here you have the strain or the time. And so you have a decrease in strain rate down to about 1% strain. And it has been tested for many, or at least what we can do in the lab, so temperature conditions, stress condition, and so on. And so Glen, he arrived, he got this curve here. And he noticed that you can relate this epsilon dot mean to the stress at which you've done your experiment, and though you get a law that is epsilon dot sigma to the power n. And this is what we call flow law. Actually, is that the law that relates to deformation? And in large-scale modeling, this is what has been used. So in the more simpler large-scale modeling, they consider that n equal 1. From the lab, we know that n equals 3. But then when we are in condition, very low stress, very low strain rate, big question mark. And so it's somehow an easy step, an easy way to say, okay, we're considering that we have here what should be a stationary creep, and we take the condition of stationary. We know from the lab that it's not stationary, because right after we have dynamic crystallization, and then this law does not really hold anymore. But that's the best we can do right now. And this is in this kind of law that we are trying to put some anisotropy by reshaping all that, so that we can have also, it's not only a law that relates to temperature, stress, but also crystallographic orientation.
Of the materials than ice that behave like ice but at different pressures or temperatures or something really unique?
No. Well, I think ice is probably one of the most viscoplastic anisotropy materials, as far as I know. But right now I'm working with some colleague in geoscience Montpellier, so Andrea Tomasi, for those who know her, and we are working on magnesium because we want an analog of olivine. So olivine is not hexagonal, it's orthotropic, but it's also highly anisotropic, and it behaves a little bit the same, so that in shear it creates some very strong single maximum, it has a lot of dynamic crystallization mechanism and so on. So we have been working together for more than 10 years, I think, with Andrea, because ice can be considered as an analog for olivine, because we can't do experiments as we can do for ice. On olivine, of course, we need much more pressure, much more higher temperature. And in the same time, ice was limited to do in situ experiments on EBSD, so on scanning electron microscope. So we are using magnesium right now. And so we are making some in situ experiment magnesium alloy, to follow the dynamic crystallization mechanism. So it's a little less anisotropic than ice, but we can make some parallel. Yep. Yes?
What is the path of the uncertainty which is linked to the real deep complexity? the damage from the friction on the bottom.
That's a very good question. I won't answer about exactly the uncertainties on the. Okay, no, I think I can answer. I won't give you figures because I don't know them. I'm not a large-scale flow modeler. I'm just using it. But what I know is that so far, one of the reasons why people didn't get so much interested about anisotropy of ice and were happy with a very simple Glen's law of this type was because people were thinking that most of the problem we had were about the bedrock interaction, what we call the friction law. So there are some friction law like the Wirtmann law for those who are familiar with friction that has been used but was very badly parameterized. And so a lot of work has been done on trying to so we are measuring, what we are measuring are mostly surface velocity. That's the only thing we have. So trying to inverse flow model from the surface velocity to get access to this friction law parameter. At least what is the best friction law we have to use and what are the parameters that we have to put. And that's the main things they've done so far. And it's okay if you consider that the rheology is homogeneous and does not count too much. But as soon as you are dealing with ice streams or glaciers that are flying fast, that have some heterogeneous condition, then the rheology may not be that homogeneous. And if you consider, I won't give you figures, I'm sorry, but I know there is papers that mention it, but if you consider an increase in fluidity of a factor 2 or 10, what is quite common for anisotropy, then you are going to make a big mistake on the way you inverse the friction law and reverse. So now the two questions are highly integrated. But then another interesting point maybe to answer is that uncertainties are, when we want to predict what ice sheets are going to become in the future climate, it was shown that the main uncertainty is, of course, in the climatic prediction, but the uncertainty on the rheology of ice or the physics of what we know and what we put in the model is not negligible neither. So this is why we are focusing a lot. Does that answer your question? Although I didn't give any figures. But I'm not doing. Crystal? Yes, more or less, yes.
So when two grains connect, the same grain in a way gets close to the same grain in different areas. In a way, the defects seem much more complex than only translational defects. And then you also showed some internal boundaries. What are those?
Okay, very interesting question because I could not talk about it. It was I didn't have enough time. But then, yes, why do we get so much dynamic recrystallization in ice only at 3% of strain, which is quite low? Is exactly what you mentioned. It's because between these grains, around this triple junction, for instance, the orientation. So the orientation is marked in color here. So here the c-axis is bluish. This one is here. Here it's greenish. So it's here. So you have some difference in crystallographic orientation. So if you consider that you only activate the basal slip systems, of course here you have a strong problem. I mean, they are not going to fit. The three slip systems are not going to fit anymore at triple junction. So how do you accommodate those strain heterogeneities that are arising here? So if you are fast enough, then you break. Okay, that's easy. But if you're low enough, then you have to reorient your crystals so that they can already, again, be favorable for basal slip deformation. Since we have very few non-basal slip systems that are being active, we have to do something. And this is why recrystallization is taking place. So we create new grains that are more favorably oriented for basal slip in this area. So they are able to accommodate this heterogeneous deformation in that part. And what we also do is we do not only create new grains, but we also make some subgrains. So we bend our crystals so that they are oriented. The basal slips is again favorable in the new configuration, because of course if you create new grains, then your stress configuration or strain configuration is going to change again. So it's a circle somehow. Does that answer your question? More.
Internal boundaries that were marked
With EBSD maybe here. So here are subgrain boundaries. So those are alignment of dislocations that will create a misorientation between this part and this part of the grain. So it's just like if you were to bend your grain in two parts. So you can have up to, here I don't know, but you know, here you can have up to 10-degree differences in orientation between the two parts due to those dislocations that are aligned in a quite proper way. So it's more nicer than in grain boundaries where it's more complicated.
Okay, so let's thank Maurine again.
Thanks for your questions.